Our galaxy holds more mysteries than we have yet to solve. We are about to journey through 25 of the Milky Way's most baffling enigmas, a tour that will forever change how you see the starry night sky. You will uncover the hidden forces shaping our cosmic home and the unanswered questions that keep astronomers awake at night. We will venture into the silent heart of a supermassive black hole and confront signals from the void that defy all explanation. What do you believe is the galaxy's greatest secret? At the very center of our vast spiral home lies its greatest and most paradoxical secret. This is Sagittarius, a star, a supermassive black hole with a mass 4 million times that of our Sun, a gravitational anchor around which our entire galaxy slowly spins. Yet for all its terrifying power, it is remarkably, almost unnervingly quiet. Most galaxies with such a monstrous core are active, blazing with energy as they devour matter, but ours slumbers. This dormancy is the first layer of the mystery. Why is our galactic heart so still? The answer may lie in a famine. There simply may not be enough gas and dust falling into its grip to power a brilliant, continuous outburst. It is a sleeping giant on a strict diet, but even a sleeping giant can have strange dreams. Periodically, and without clear warning, Sagittarius, a star, awakens with a violent burp. It erupts in sudden, powerful flares of X-ray and infrared light that can brighten its immediate vicinity by a factor of 100 in mere minutes. These outbursts are brief and chaotic, defying our attempts to predict them. What triggers these tantrums? Is it a stray asteroid ripped apart by tidal forces, or perhaps a clump of magnetically tangled gas finally crossing the point of no return? Each flare is a cryptic message from the edge of space-time that we are only beginning to decode. Our view of this enigmatic object transformed with the release of the first direct image from the Event Horizon Telescope. That now iconic, blurry orange donut of light confirmed Einstein's predictions in stunning detail, showing the shadow of the black hole's event horizon against the swirling, superheated plasma around it. Yet the image raised as many questions as it answered. It revealed a puzzling asymmetry in the brightness of the ring, hinting at complex magnetic fields and violent rotation we do not fully understand. Adding to the strangeness are the peculiar objects dancing perilously close to this cosmic abyss. Take the mysterious cloud known as G2. Astronomers watched captivated as it made its closest approach to Sagittarius, a star, expecting a spectacular display as the black hole tore it apart and feasted. But G2 did something extraordinary. It stretched, distorted, and then survived. It sailed right on by. This resilience suggests G2 is not a simple gas cloud, but perhaps a star shrouded in dust or something else entirely, its true nature still cloaked by the galactic center's murk. These odd orbital dancers, along with the silent giant they circle, form a cryptic ballet at the Milky Way's core, a performance whose rules we are still desperately trying to learn. That quiet giant at the galactic center may have a violent past, and we are staring at the evidence. Stretching far above and below the Milky Way's disk are two colossal, ghostly orbs of energy known as the Fermi bubbles. Discovered just over a decade ago by the Fermi Gamma-Ray Space Telescope, these structures are not made of stars or dust, but of seething gamma rays and X-rays. They are essentially a pair of the largest, most energetic balloons imaginable, each one reaching a staggering 25,000 light-years from the galactic plane. To grasp their scale, picture our entire galaxy, a spiral disk 100,000 light-years across. Now imagine two immense spheres of radiation, one north and one south, together forming a figure 8 that dwarfs the visible galaxy itself. They are a permanent, faint glow in the high-energy sky, a cosmic scar that tells a story of unimaginable power. But what created them? The leading theory points directly back to our dormant black hole, Sagittarius, a star. Astronomers suspect that several million years ago, the sleeping giant woke up in a truly catastrophic way. it may have experienced a titanic feeding frenzy, devouring an enormous amount of gas and star matter in one go. The energy from that meal would have been funneled into two opposing jets, erupting perpendicular to the galactic disk and inflating these gigantic bubbles with ultra-fast particles. It would have been a brief, blinding eruption, a galactic-scale belch that echoed for eons. Another possibility is a different kind of frenzy, not from the black hole but from the bustling region around it. A period of intense, rapid star formation and subsequent supernova explosions could have collectively blown these bubbles with a stellar wind of unprecedented force. The debate is fierce because the evidence is subtle and ancient. We are essentially cosmic archaeologists trying to reconstruct a single cataclysmic event from the faint, lingering afterglow it left behind. The bubbles are there, clear as day in gamma-ray light, but their origin story remains one of the galaxy's most profound and unresolved whispers. This faint echo of a past cataclysm is not the only force pulling strings behind the galactic curtain. Our entire neighborhood is in motion, caught in a river of gravity we cannot see. For decades, astronomers mapped the expansion of the universe and expected to see galaxies drifting apart in a stately, predictable flow. Instead, they found our local group, which includes the Milky Way and Andromeda, is rushing headlong toward a specific point in the constellation Centaurus at an astonishing speed of over 2 million kilometers per hour. Something with incomprehensible gravity is pulling us and everything nearby toward it. They named this mysterious focal point the Great Attractor, discovering it was a feat of cosmic deduction. Scientists were not looking at a bright object, but at the subtle drift of thousands of galaxies, all showing a shared, peculiar motion that betrayed the presence of a hidden, massive source of gravity. It was like watching leaves on a river all flowing in the same direction and realizing there must be a colossal waterfall just beyond the horizon. But when they pointed their telescopes toward that spot in the sky, they saw almost nothing. The Great Attractor lies directly behind the crowded, dusty plain of our own Milky Way, in a region astronomers call the Zone of Avoidance, our galaxy's own bustling disk, filled with stars, gas, and opaque dust, acts like a brilliant smokescreen, completely obscuring our view of the universe beyond. It is the ultimate cosmic blind spot, hiding what may be one of the most significant structures in our local universe. Peering through this galactic fog with X-ray and radio telescopes has slowly revealed parts of the truth. At the heart of the Great Attractor lies the Norma Cluster, a dense gathering of thousands of galaxies, a gravitational anchor of immense proportions. But here is the twist: the Norma Cluster is massive, but it does not seem massive enough. Its gravity alone cannot account for the tremendous pull we are experiencing. This realization deepened the mystery. Is the Great Attractor not one single object, but the combined pull of many superclusters in that direction? The current leading theory suggests we are being swept up in something even grander. A vast cosmic current flowing toward the Shapley supercluster, the largest known concentration of matter in our observable universe. The Great Attractor, then, may be just a waypoint, a signpost on a much longer journey. We are caught in a gravitational tide so vast we can only infer its source, a reminder that even as we map the stars, the most powerful forces shaping our cosmic path often remain hidden in the shadows. The pull of hidden giants is not the only way the galaxy speaks to us. Sometimes it shouts just once and leaves us forever wondering. On a quiet August night in 1977, a radio telescope at Ohio State University known as the Big Ear was performing its routine scan of the cosmos. It was listening to a specific, narrow band of radio frequencies, a channel scientists believed would be ideal for interstellar communication because it is naturally quiet, dominated only by the faint whisper of hydrogen, the universe's most common element. Suddenly, the needle jumped. For 72 breathtaking seconds, a powerful, focused signal burst through the silence. It was not random static. It was concentrated at exactly the frequency of hydrogen, 1420 MHz, and it matched the precise profile astronomers expected from an artificial extraterrestrial transmission. When researcher Jerry Amon reviewed the computer printout days later, he saw the alphanumeric code representing the signal's intensity, 6 letters and numbers so strong he circled them in red pen and wrote a single monumental word in the margin: "Wow." That annotation gave the signal its immortal name. The WOW signal remains, to this day, the most compelling and enigmatic candidate for a message from another civilization ever detected. Its characteristics were perfect, a beacon that seemed to say, "We are here." Yet after that one brilliant flash, it never returned. Despite decades of targeted searches by countless telescopes listening to the exact same patch of sky in the constellation Sagittarius, the silence has been absolute. The hunt for an explanation has led down many frustrating paths. Some suggested it could have been a reflection of a human signal bouncing off a piece of space debris. Others proposed natural cosmic beacons like a pulsar, a rapidly spinning neutron star. But pulsars pulse, they blink on and off with metronomic regularity, and the WOW signal was a single, smooth surge. More recently, a theory pointed to comets, suggesting the hydrogen in their tails could emit a similar frequency. The problem is, the two comets proposed were not in that precise part of the sky on that night in 1977. Every natural explanation so far has a flaw, a detail that does not quite fit the pristine data on Jerry Amon's printout. This singular event sits alone in the history of astronomy, a 72-second mystery that has fueled our imagination and our scientific rigor for nearly half a century. It is a ghost in the galactic machine, a whisper that proves the universe is capable of sending a signal we would recognize, and that we might only get one chance to hear it. The profound silence after the WOW signal stands in stark contrast to another, far more common cosmic shout. Across the universe, brilliant flashes of radio energy erupt and vanish in less time than it takes to blink. These are fast radio bursts, or FRB, and for years they were the ultimate cosmic flash in the pan, appearing from deep space without warning and never repeating. The mystery deepened when we found the repeaters. FRB 121102 was the first to be heard again and again, its bursts tracing back to a tiny, turbulent dwarf galaxy 3 billion light-years away. Then came FRB 180916, which revealed an astonishing pattern, a 16-day cycle of activity with 4 days of frantic bursts followed by 12 days of radio silence. These were not random explosions, they were behaviors, clues written in a language of pure energy we are struggling to translate. The breakthrough came from within our own galactic backyard. In April 2020, a magnetar in the Milky Way, known as SGR 1935+2154, did something unprecedented. This highly magnetized, spinning stellar corpse unleashed a burst of radio waves so powerful it would have been detectable from another galaxy. For the first time, we had a smoking gun, a local source for an FRB. The link between magnetars and at least some of these bursts seemed clear. Picture a magnetar, a city-sized neutron star with a magnetic field a quadrillion times stronger than Earth. This field is under unimaginable stress, and when the star's crust cracks under the strain, it can trigger a starquake, releasing a cataclysmic flare of energy across the electromagnetic spectrum, including a blinding pulse of radio waves. But the discovery solved one puzzle while creating others. If magnetars are the source, why do only a tiny fraction of the thousands known produce FRBs? And how do we explain the precise clockwork periodicity of a repeater like FRB 180916? Such a clean cycle suggests an orbital influence. Perhaps the magnetar is in a binary system with another star, its bursts modulated by a companion's gravity or by regularly plunging through a disk of debris. This implies a stunning diversity of engines behind what we once thought was a single phenomenon. Some FRBs could be from isolated magnetars having catastrophic seizures. Others might be from magnetars in complex stellar dances, and still others, especially the one-off bursts from the cosmic dawn, could be the final, desperate signals from exotic events we have not yet dreamed of, like colliding neutron stars or evaporating primordial black holes. The galaxy has shown us one way to make an FRB, but in doing so, it whispered that the true story is far more complex and wondrous. Even as we map brilliant bursts and colossal structures, a deeper, more fundamental absence haunts our understanding of the galaxy. We are missing the very stuff we are made of. This is the missing baryon problem, a cosmic accounting error that strikes at the heart of what we think the Milky Way is. Baryons are the ordinary matter that makes up everything you can see and touch, from stars and planets to your own body. In the early universe, we can measure with incredible precision how much of this normal matter existed. Yet when astronomers take a census of the Milky Way and its nearby cosmic neighborhood today, the numbers do not add up. A staggering 30 to 50% of the baryonic matter that should be here, that we know was created in the Big Bang, has simply vanished from our ledgers. It is as if you carefully counted all the bricks delivered to build a house, but when you finished, half of them were gone, with no rubble left behind. So where did it all go? The leading suspect is not a place of darkness, but one of faint, diffuse heat. Theorists believe the missing matter is hiding in the form of the warm, hot intergalactic medium, or WIM. Picture this not as a cloud, but as a vast, tenuous web of superheated gas, filaments stretching between galaxies in the cosmic web. This gas is so hot at millions of degrees that it does not glow in visible light. It emits only a faint whisper of X-rays. It is also so incredibly spread out that a cubic meter of this space might contain only a single atom. Detecting it is like trying to see the thin, hot steam rising from a cup of coffee in a massive, foggy stadium. Our best evidence for the WIM comes from using distant, brilliant quasars as cosmic flashlights. As their light travels billions of light years to reach us, it passes through these filaments. The superheated gas within them absorbs very specific wavelengths of that light, leaving minuscule fingerprints in the quasar's spectrum. It is painstaking, indirect detective work, and while we have found some of these fingerprints, the total amount of matter they account for is still uncertain. Other suspects lurk closer to home. A significant portion could be hiding right in our own galactic halo, the vast spherical region of sparse stars and dark matter that surrounds the Milky Way's luminous disk. This halo could be filled with enormous, faint clouds of warm gas, or with rogue planets and failed stars too dim for our telescopes to see. The truth is likely a combination, a cosmic hide and seek where the ordinary matter of the universe has been scattered into forms so elusive they have slipped through our observational nets for decades. Solving this mystery is not just about balancing a ledger, it is about understanding the complete life cycle of the galaxy itself. Where did this matter go, and what processes swept it into the shadows? The answer will tell us the ultimate fate of the material that once swirled in the nebulae that gave birth to stars like our own sun. The missing ordinary matter is just a fraction of a far deeper cosmic secret. Surrounding our entire galaxy, and indeed every galaxy we see, is a vast, invisible sphere of influence that outweighs all the stars, planets, and gas combined. This is the dark matter halo, the single greatest unsolved puzzle in modern astrophysics. We know it is there because we can see its ghostly hand gripping everything within it. Stars on the outer edges of spiral galaxies like ours orbit far too quickly. According to the laws of gravity and the amount of visible mass we can see, these distant stars should be drifting along at a leisurely pace like cars on the outskirts of a city. Instead, they are racing around as if the entire downtown core were packed with invisible skyscrapers. The only way to explain these flat rotation curves is to propose a colossal amount of unseen matter, a dark halo whose gravity holds the speeding stars in their tracks. Another line of evidence comes from a cosmic magnifying glass, gravitational lensing. When light from a distant galaxy passes near a massive object like a galaxy cluster, the cluster's gravity bends the light, distorting and magnifying the background galaxy's image. But the amount of bending we observe often requires far more mass than the cluster's visible stars and gas can provide. The lens itself seems to be made of something we cannot see, something that permeates the entire cluster and extends far beyond its luminous boundaries. So what is this mysterious substance? We have ruled out the obvious candidates. It is not made of black holes, as extensive surveys have not found enough of them. It is not composed of dim, failed stars called brown dwarfs or rogue planets, collectively known as massive compact halo objects or MACHO. Searches for these objects have come up far short of the required mass. Dark matter must be something far more exotic, something that does not interact with light at all, only making its presence known through gravity. The leading theoretical candidate for decades has been the WIMP, the weakly interacting massive particle. These hypothetical particles would be heavy, slow-moving, and only rarely bump into ordinary matter. To find them, scientists have built exquisitely sensitive detectors deep underground, in mines and tunnels shielded from cosmic rays. These experiments, with names like LUX, Xenon, and Panda X, wait in profound silence for the once-in-a-lifetime tremor that might be a WIMP striking an atomic nucleus. Yet so far, after years of searching, the detectors have remained quiet. This silence has brought another candidate to the forefront, the action. Trillions of times lighter than an electron, the action was originally proposed to solve a different puzzle in particle physics. In theory, these ultralight particles could flood the galaxy, behaving more like a pervasive, invisible field than discrete particles. Experiments like ATMS are using powerful magnetic fields to try and coax these ghostly particles into revealing themselves as a faint radio signal. The implications of this search are staggering. To directly detect dark matter would be to touch a fundamental component of the universe that has shaped cosmic history from the very beginning. It is the hidden scaffolding upon which galaxies were built, the gravitational glue that allowed stars to form in the first place. Solving this mystery would not just fill a gap in our equations, it would open a door to a completely new realm of physics, revealing a hidden layer of reality that has been with us all along. But this invisible scaffolding of dark matter does more than just hold galaxies together. It shapes the grand architecture of the universe on the largest scales. Far beyond the halo of the Milky Way, astronomers have mapped a cosmos that looks less like a uniform scatter of stars and more like a vast, frothy web. Galaxies cluster along luminous filaments which intersect at dense nodes, all separated by staggering, empty chasms. The most famous of these cosmic voids is a place of profound emptiness known as the Boots Void. Discovered in the 1980s, this spherical region of space is a staggering 330 million light-years across. To understand that scale, if you place the Milky Way at one edge, the most distant galaxies on the other side would be so far away their light has been traveling for over 300 million years to reach us. And within that incomprehensible volume, there are almost no galaxies. Where a typical region of space that size would contain thousands, perhaps tens of thousands of galaxies, the Boots Void holds only a few dozen, lost like lonely ships in an ocean of nothingness. Its existence forces a difficult question. How does the universe carve out such perfect, colossal spheres of near nothing? The answer likely lies in the very earliest moments of creation. Tiny quantum fluctuations in the primordial soup of the Big Bang were stretched to cosmic proportions by inflation. Where those fluctuations were denser, matter pooled under gravity, eventually forming the galaxies and clusters we see today. Where they were less dense, matter drained away, leaving behind these immense, empty bubbles. The Boots Void is not a hole punched through the universe, it is a fossil, a preserved imprint of the universe's subtle infancy. This grand cosmic web directly relates to our own place in the Milky Way. We do not live in a uniformly dense star field. Our solar system resides in what astronomers call the local arm, or the Orion Spur, a relatively minor bridge of stars and gas nestled between two of the galaxy's majestic major spiral arms, the Sagittarius arm and the Perseus arm. Why are we here in this quieter suburb rather than in the brilliant, chaotic heart of a major arm? The spiral arms themselves are not permanent structures made of the same stars. They are traffic jams in the galactic disk. Think of them as cosmic sound waves, but moving through the collective gravity of the galaxy's stars and gas. These are density waves. As a wave passes through, it compresses the interstellar gas, triggering the birth of brilliant, short-lived blue giant stars that light up the arm. The stars themselves, including our Sun, move in and out of these waves as they orbit the galactic center. Our Sun has likely passed through several spiral arms in its 4.5 billion-year lifetime. The mystery is how these patterns persist for billions of years without winding up into a tight knot or dissipating entirely. What process continuously regenerates these elegant spirals? The leading theory points again to gravitational interactions, not just with dark matter, but with satellite galaxies and the central bar of the Milky Way. Their subtle, persistent tugs may act like a steady hand on a spinning plate, maintaining the delicate balance of the density wave, yet the precise mechanics remain elusive. We are left contemplating a galaxy that is both a dynamic, swirling river of stars and a structure of astonishing longevity. Its grand design etched across 100,000 light-years, a design whose maintenance is one of its most enduring and beautiful mysteries. While the spiral arms maintain their elegant dance, some stars break free from the galaxy's rhythm entirely. These are hypervelocity stars, stellar projectiles flung across the Milky Way at over 1 million miles per hour, speed so tremendous they are on a one-way trip into the intergalactic void. They are cosmic escape artists, and their origin story is a tale of gravitational betrayal at the most violent place imaginable. The leading theory points directly to the monster at our galaxy's heart, Sagittarius A star. Imagine a pair of stars, a binary system, orbiting each other in a stable dance as they fall toward the central black hole. If they swing too close, the black hole's immense gravity can perform a brutal act of stellar kidnapping. It captures one star, pulling it into a tight, doomed orbit, while its companion is violently slingshotted away, catapulted outward like a stone from a sling. This three-body interaction imparts an unbelievable velocity, sending the ejected star racing toward the galactic frontier. We have caught one of these fugitives red-handed. The star known as S5HVS1 is a pristine example, a sun-like star screaming through the galaxy at roughly 4 million miles per hour. By tracing its path backward across the sky, astronomers found its trajectory leads straight back to the galactic center, a perfect match for the black hole ejection model. It is a stellar bullet with a clear fingerprint on it, yet this elegant explanation may not account for every runaway. Could other cosmic launchers exist? One compelling alternative involves a different kind of stellar catastrophe, the supernova explosion in a tight binary system. If one star explodes, the sudden loss of mass can catastrophically unbalance the gravitational bond, releasing the surviving companion like a released spring, sending it careening into space. Another, more speculative possibility involves the invisible hand of dark matter. Could a dense clump of dark matter passing through a star system transfer enough momentum to kick a star loose? Or could an encounter with a rogue intermediate mass black hole wandering unseen through the galactic disk provide the necessary gravitational punch? Each hypervelocity star we discover is a forensic clue. Their speed, their composition, and their trajectory tell a story of their violent past. By cataloging these stellar exiles, we are piecing together a map of the galaxy's most extreme gravitational events, a history written not in rock, but in the paths of suns flung from their homes. Even stars flung from the galaxy cannot escape the subtle grip of gravity, a force we are still struggling to fully understand. This struggle became profoundly personal with two of our own robotic ambassadors, the Pioneer 10 and 11 spacecraft. After completing their historic missions to Jupiter and Saturn, these hardy probes continued on a one-way journey into interstellar space. Yet as they drifted farther from the Sun, tracking their precise position revealed something deeply unsettling. Both spacecraft were experiencing a tiny, unexplained deceleration, a constant, gentle tug back toward the inner solar system. This minuscule drift became known as the Pioneer anomaly. The effect was incredibly small, less than a billionth of the gravity you feel standing on Earth, but it was persistent and identical for both probes, which were millions of miles apart. For scientists, this was an irresistible cosmic clue, a potential whisper of new physics. Could it be evidence that our theory of gravity, Einstein's general relativity, needed a slight adjustment over vast distances? Or perhaps it was a hint of unseen matter in the solar system, a diffuse halo of dark matter subtly breaking the spacecraft. The mystery ignited a decades-long investigation, a masterclass in cosmic detective work. Researchers combed through decades of telemetry data, building increasingly sophisticated models of the spacecraft themselves. They had to account for every conceivable onboard effect. Was there a tiny gas leak from a thruster providing a minute push? Could the spacecraft's radioactive power source, the plutonium in its thermoelectric generators, be emitting particles that acted like a weak rocket? Each possibility was meticulously examined and one by one ruled out. The answer, when it finally emerged, was both brilliant and humbling. A team of scientists led by Slava Turyshev performed a Herculean feat of data archaeology, recovering old telemetry and even original design blueprints. They built a complete thermal model of the Pioneer spacecraft and discovered the culprit was not a mysterious force but simple, uneven heat. The probe's electricity was generated by the decay of plutonium, and that process created waste heat. This heat radiated away from the spacecraft, but not perfectly evenly. More heat was emitted from the back of the dish-shaped antenna, which faced toward the Sun, than from the front. This anisotropic thermal radiation created a tiny photon pressure, an immeasurably faint but constant push, acting like a brake slowing the Pioneers down. The case was largely closed, a triumph of meticulous engineering analysis over exotic physics. Yet, a whisper of the anomaly persists. Some researchers point out that while thermal radiation explains most of the drift, there remains a tiny residual effect in the data, a sliver of deceleration that the models do not perfectly capture. It is a reminder that in the vast quiet of deep space, even the most carefully designed experiments can hold onto a final secret. The Pioneer anomaly teaches us that the universe's greatest mysteries are sometimes solved not by discovering something new out there, but by finally understanding the intricate details of the machines we send to explore it. The Pioneer's quiet deceleration reminds us that even our own cosmic backyard holds profound mysteries, and one of the sharpest lies just beyond Neptune. This is the Kuiper Cliff, a sudden and dramatic boundary where the outer solar system seems to simply end. The Kuiper Belt, that vast donut of icy debris left over from the solar system's formation, extends from Neptune's orbit out to about 50 astronomical units, where 1 astronomical unit is the distance from Earth to the Sun. But beyond that 50 mark, the population of objects plummets. It is as if someone drew a line in the cosmic sand and said nothing beyond this point. This is not what astronomers expected. Models of our solar system's birth suggest the primordial disk of gas and dust should have thinned out gradually, leaving a sparse but steady population of icy bodies extending much farther into the void. The cliff's existence is a glaring anomaly in our local space, and its explanation may be written in the broader history of the Milky Way. One compelling suspect is a hidden world, the hypothetical planet 9. This would not be a small, icy body, but a true giant, perhaps 5 to 10 times the mass of Earth, orbiting hundreds of astronomical units from the Sun. Its immense gravitational influence over millions of years could have sculpted the outer Kuiper belt, clearing a vast region and shepherding objects into peculiar clustered orbits. The search for this phantom planet is ongoing, a celestial detective story trying to explain the strange architecture at our solar system's edge. Yet another possibility reaches back to the Milky Way's chaotic nursery. Our Sun was born in a dense stellar cluster alongside thousands of other stars. In that crowded environment, a passing sibling star could have ventured close to our infant solar system. The gravitational tide from that close encounter would have been catastrophic, stripping away the outer reaches of the protoplanetary disk and carving the sharp edge we see today. That passing star is long gone, lost to the galactic rotation, leaving only this fossilized boundary as evidence of a dramatic close call billions of years ago. The third explanation is more subtle but equally profound. It suggests the cliff is not a scar from an event but a birthmark. The primordial cloud that collapsed to form our Sun may have had a specific density profile, or perhaps the process of planet formation itself consumed the available material out to that 50O limit, leaving a natural and abrupt edge. Each of these theories speaks to processes that are likely universal. If a hidden planet can sculpt our Kuiper belt, then such unseen giants probably orbit countless other stars, shaping their debris disks in ways we are only beginning to model. If a stellar flyby carved our solar system, then such gravitational graffiti must be common throughout the galaxy's star-forming regions. This local mystery, therefore, is a window. The Kuiper Cliff is not just a curious feature of our home. It is a single data point hinting at the dynamic and often violent gravitational storytelling that defines the evolution of planetary systems across the Milky Way. Our own solar system's sharp edge is a reminder that location is everything in the cosmos, and this principle may decide the ultimate question of life itself. We orbit within what astronomers call the galactic habitable zone, a theorized region within the Milky Way where conditions are just right for complex life to arise and survive. This is not a single, well-defined ring, but a complex, evolving band shaped by three deadly forces and one essential gift. The first threat is the galactic center. Venture too close to that brilliant, crowded core, and you are bombarded by intense radiation from the supermassive black hole and the dense clusters of stars constantly going supernova. It is a stellar metropolis with a permanent, lethal fireworks display. The second threat comes from those very fireworks. Supernova, the catastrophic explosions of massive stars, sterilize vast regions of space with lethal bursts of gamma rays and X-rays. A planet too close to such an event, or in a spiral arm where massive star formation is rampant, could have its atmosphere stripped away and its surface scoured clean. So a safe location must be in a relatively quiet suburb, away from the bustling, dangerous downtown and the chaotic construction zones of the major spiral arms. Yet a planet cannot be too isolated either. The third critical ingredient is metallicity, the abundance of elements heavier than hydrogen and helium. These elements, forged in the hearts of stars and scattered by supernova, are the building blocks of rocky planets like Earth and the chemistry of life itself. A star system born too early in the galaxy's history, from pristine gas with low metallicity, would lack the raw materials to form terrestrial planets. Therefore, the sweet spot is a region that has been enriched by previous generations of stars, but is not so active that it is constantly bathed in sterilizing radiation. Our Sun seems to occupy this privileged zone. We are about 27,000 light-years from the chaotic center, orbiting in a relatively quiet spur between major arms, and our solar system formed from gas enriched with heavy elements by stars that died billions of years before. But are we uniquely special, or is this galactic habitable zone a broad common band? The mystery deepens when we consider time. This zone is not static. As the galaxy evolves, producing more heavy elements, the region conducive to life may actually expand outward from the center over billions of years. We might be living in a particularly fortunate era, a cosmic springtime where metallicity is high enough for complex chemistry, but the frequency of catastrophic supernova in our neighborhood has temporarily quieted. Pinpointing exactly where and when these Goldilocks conditions align is one of the great challenges of modern astrobiology. It forces us to ask a profound question: is our peaceful, life-bearing orbit a rare cosmic accident or a common feature of spiral galaxies across the universe? Our galactic neighborhood's delicate balance for life depends on chemistry, but a fundamental ingredient in that cosmic recipe is mysteriously missing. This is the lithium problem, a quiet but profound disagreement between the story of the universe's birth and the oldest stars we can see. According to our most precise models of the Big Bang, the first few minutes of cosmic creation forged the universe's original supply of hydrogen, helium, and a tiny trace of lithium. Specifically, the isotope lithium-7. The physics of that primordial nuclear fusion is so well understood that we can calculate, with remarkable confidence, exactly how much of this light element should have been scattered across space. Yet when astronomers point their telescopes at the most ancient stars in the Milky Way's halo, the pristine fossils that formed from nearly pure Big Bang material, the numbers do not match. These ancient suns contain only about 1/3 of the lithium that our cosmic birth certificate says they should. It is as if we had a perfect recipe for a cake, followed it exactly, but when we taste it, a key spice is only present at a fraction of the promised amount. This is not a minor accounting error, it is a direct challenge that pits cosmology against stellar astrophysics. Where did all that primordial lithium go? One possibility is that our understanding of the Big Bang's nuclear kitchen is incomplete. Perhaps unknown particles or exotic physics in the universe's first fiery moments altered the nuclear reaction rates, producing less lithium than our standard models predict. Another line of investigation looks at the stars themselves. Could these ancient halo stars, over their immense multi-billion-year lifetimes, have somehow destroyed or hidden the lithium in their atmospheres? Stellar models suggest that as these stars churn their internal gases, lithium, which is fragile and easily broken apart at high temperatures, could be dragged down into hotter layers and destroyed. But the observed stars are some of the coolest and least active we know, making this explanation difficult to square with their calm nature. The most intriguing possibility invokes something entirely new. What if exotic particles, like certain types of dark matter, interacted with the cores of these ancient stars? Such interactions could provide an extra source of heat, altering the star's internal structure and creating deeper currents that would carry surface lithium down to be incinerated. This would mean the oldest stars in our galaxy are not just cosmic fossils, but also detectors, recording the faint whispers of dark matter's influence over billions of years. Solving the lithium problem requires listening to these ancient stellar voices, and their quiet testimony suggests that either our universe's first moments held a secret, or its oldest structures are keeping one. The clockwork of our solar system's orbit may hold the key to Earth's most catastrophic chapters. Every 250 million years, our Sun completes a single grand circuit around the galactic center. This immense span of time is known as a galactic year, a celestial rhythm so slow that in the entire history of complex life on Earth, we have only completed about 20 such orbits. A provocative and chilling idea suggests this cosmic clock might be ticking in sync with death on our planet. The hypothesis proposes that mass extinctions, those terrible events that have repeatedly scrubbed the slate of life, could be linked to our solar system's periodic passage through the Milky Way's spiral arms. As we enter these denser regions of stars and gas, the gravitational environment grows more turbulent. The theory suggests this could disturb the distant cloud of icy bodies at the solar system's edge, the Oort cloud, sending a shower of comets plunging inward. Such a comet storm, lasting hundreds of thousands of years, could dramatically increase the odds of a civilization-ending impact, like the one that doomed the dinosaurs 66 million years ago. There is a second, equally grim mechanism tied to the spiral arms. These regions are stellar nurseries, bustling with the birth and explosive death of massive stars. Passing through an arm could statistically increase our exposure to a nearby supernova, a stellar detonation close enough to bathe Earth in lethal radiation, potentially stripping our protective ozone layer and triggering a collapse of the food chain. The allure of this idea is its elegant, cyclical nature. It connects the grand architecture of the galaxy directly to the fossil record beneath our feet. Some researchers have pointed to tentative correlations, noting that several major extinction events appear to be roughly spaced every 30 to 35 million years, a time frame that could align with our solar system's vertical oscillation through the galactic plane or its encounters with spiral arms. The evidence, however, is fiercely contested. The galactic year is not a metronome, and the spiral arms are not static, rigid structures. Our sun's motion is complex, and the timing of our passages through arms is difficult to reconstruct with precision over hundreds of millions of years. Furthermore, the Earth's own geological record is an incomplete and brutally difficult book to read. Pinpointing the exact timing of an extinction event and definitively linking it to an impact or radiation pulse is an enormous challenge. Many paleontologists argue that the primary drivers of mass extinctions are homegrown, the devastating results of monumental volcanic eruptions, drastic climate change, or the complex interplay of life itself. The galactic extinction hypothesis remains on the fringe, a spectacular story that is difficult to prove but impossible to entirely dismiss. It forces a profound perspective that the fate of all life on our vibrant blue world may be written, in part, by our silent journey through the star-crowded lanes of the Milky Way. This silent rhythm of possible extinction is governed by forces far more subtle than gravity alone. Woven through the very fabric of our galaxy, between the stars and within the clouds, is an invisible, tangled web of magnetic fields. We cannot see them directly, but their influence is everywhere. They guide the paths of ultra-high energy cosmic rays, shape the birth of new stars, and paint the sky with faint, polarized light. Mapping this ghostly lattice is a triumph of indirect observation. Astronomers act as cosmic surveyors using two primary tools. The first is starlight itself. As light from distant stars travels through the Milky Way, it passes through clouds of dust that are aligned by these magnetic fields. This alignment polarizes the light, twisting it in a specific direction. By measuring the polarization of light from millions of stars, we can trace the orientation of the magnetic fields along our line of sight, building a three-dimensional map of their threads. The second tool listens to a different kind of emission, synchrotron radiation. This is the radiant glow given off when high-speed electrons, often accelerated by supernova shocks, spiral around magnetic field lines. It is a non-thermal hum that fills the radio spectrum, and its intensity and polarization reveal the strength and structure of the magnetic fields in the emptiest regions of space. Together, these methods reveal a stunningly complex picture. The Milky Way's magnetic field is not a simple, neat bar magnet. It is a chaotic tapestry with large-scale patterns following the spiral arms, but also filled with loops, filaments, and turbulent knots at smaller scales. The grand mystery is not just what it looks like, but how it came to be and why it persists. One leading theory points to a cosmic dynamo. Just as the churning, molten iron in Earth's outer core generates our planet's magnetic field, the rotation of the galaxy's ionized gas, stirred by the birth and death of stars, could amplify and sustain these fields over billions of years. It is a self-perpetuating engine where a weak seed field gets twisted and stretched by galactic rotation into the powerful structures we detect. another idea gives a more violent starring role to supernova explosions. When a massive star dies, its shockwave can compress and amplify magnetic fields in its wake, while also flooding the interstellar medium with energetic particles that make the fields light up. The galaxy might be in a constant state of magnetic repair, with each stellar catastrophe weaving new threads into the cosmic web. A more profound possibility is that these fields are primordial, a fossil imprint from the universe's infancy, stretched to galactic scales during the epoch of inflation. They would be a living relic of the first moments of time, frozen into the fabric of space itself. Why does this matter? These invisible fields are galactic infrastructure. They govern the acceleration and confinement of cosmic rays, those mysterious high-energy particles that constantly bombard our planet. They also provide crucial pressure within vast clouds of gas, resisting gravitational collapse and thus controlling the pace and efficiency of star formation. A galaxy with a different magnetic blueprint might spin out stars at a different rate, or not at all. Unraveling the origin of the Milky Way's magnetic web is therefore essential to understanding the very heartbeat of our cosmic home, a silent, pervasive force that writes its rules in light we must learn to see. These invisible magnetic threads are highways for the universe's most powerful natural accelerators. Streaking through the galaxy are particles carrying more energy than anything we can produce on Earth, cosmic bullets with the punch of a major league fastball. These are ultra-high energy cosmic rays, and their source is one of the Milky Way's most enduring and violent secrets. Detecting them is a feat of indirect observation. When one of these rare, monstrous particles, often a single proton, slams into the top of Earth's atmosphere, it triggers an explosive cascade, a shower of billions of secondary particles that rain down over an area the size of a city. Ground-based observatories like the Pierre Auger Observatory in Argentina use vast arrays of water tanks or fluorescence detectors to capture the faint glow and footprint of these giant air showers. The particle itself is long gone, annihilated in that first collision, so we must reconstruct its original identity and energy from the debris. The greatest challenge is not detection but navigation. Cosmic rays are charged particles, and as they cross the galaxy, they are deflected and scrambled by those pervasive interstellar magnetic fields. By the time one reaches us, its path is a hopelessly tangled mess, like trying to trace a single drop of water back to its origin in a hurricane-swept ocean. We cannot simply point a telescope back along a straight line to see where it came from. To find their sources, astronomers must become statisticians, looking for faint patterns in the arrival directions of thousands of these events, hoping for a slight excess pointing back to a particular region of the sky. Within our own galaxy, the prime suspects are sites of extreme violence and magnetic chaos. Supernova remnants, the expanding shells of gas from exploded stars, are leading candidates. The Cygnus Loop, a beautiful, wispy nebula that is the wreckage of a star that died millennia ago, is a perfect example. Theorists believe the turbulent shock waves from these explosions can act as natural particle accelerators, a process called Fermi acceleration. A charged particle can bounce back and forth across a shock front, gaining a little energy each time, like a surfer repeatedly catching a wave until it is hurled forward at a tremendous fraction of the speed of light. Another compelling galactic source is the magnetar. With magnetic fields thousands of times stronger than a typical neutron star, these objects could potentially accelerate particles to extreme energies through starquakes or through the immense voltages generated by their spinning, magnetized crust. Yet a fierce debate rages. Are the very highest energy cosmic rays, those with energies millions of times beyond what the Large Hadron Collider can produce, even from our galaxy at all? At such unimaginable energies, particles should be somewhat less affected by magnetic fields, and their paths might point more truly. Intriguingly, the arrival directions of the most extreme events do not seem to cluster along the Milky Way's disk. Instead, they appear to come from all directions, suggesting an extragalactic origin. Their sources could be phenomenally powerful engines far beyond our galaxy, like active galactic nuclei with their jets of plasma, or cataclysmic collisions between entire galaxies. The puzzle of their acceleration is therefore twofold. We must explain a population of lower-energy cosmic rays clearly born within the Milky Way's furious stellar foundries, and a separate, even more extreme population that seems to hail from the deepest voids of intergalactic space. Each particle that strikes our atmosphere is a messenger from a cosmic battlefield, but its letter of origin has been torn to pieces by a magnetic storm along the way. The search for cosmic signals is a story of hope and relentless skepticism, a balance perfectly illustrated by a star 95 light-years away. In the constellation Hercules lies a sun-like star known as HD 164595. In 2015, the RATAN 600 radio telescope in Russia detected something extraordinary from its direction. A powerful, narrow-band radio burst at a frequency of 11 GHz. This was not the random hiss of cosmic noise. The signal was strong, and it came from a specific point where a star very much like our own sun resides. For a brief, electrifying moment, it ticked several boxes for a potential technosignature, an artificial broadcast from another civilization. The frequency was unusual for natural astrophysical processes, and its intensity suggested a transmitter of staggering power, potentially a Type II civilization on the Kardashev scale harnessing the energy of its entire star. The news ignited the SETI community, and telescopes around the world swiftly turned to listen for a repeat. The silence that followed was deafening. No follow-up observation, not even the ultra-sensitive Allen telescope array, could detect the signal again. That singular, unrepeated nature was the first major clue that this was not a beacon from the stars. The investigation turned from the cosmic to the terrestrial. Scientists meticulously analyzed the signal's characteristics and the telescope's field of view. A compelling and likely explanation emerged. The signal's properties closely matched those of a military satellite or other human-made transmitter passing through the telescope's beam. The RATAN 600 has a unique, wide field of view, making it superb for surveys but also susceptible to picking up signals from overhead objects. It was a classic case of cosmic confusion, a whisper from our own technological clutter mistaken for a shout from the void. HD 164595 stands as a critical case study in the modern search for extraterrestrial intelligence. It highlights the immense difficulty of the task. Our galaxy is now filled with the radio whispers of our own civilization, from satellites and radar and everyday communications, creating a cacophony we must learn to filter out. Every intriguing signal must pass the ultimate test, repeatability and verification from multiple, independent observatories. This event did not diminish the search, it refined it. It reinforced the rigorous protocols scientists follow and underscored that the greatest discoveries will not come from a single, spectacular blip, but from a persistent, verifiable pattern that nature simply cannot produce. The mystery of HD 164595 was solved, but the larger quest it represents continues, a meticulous sifting of the galactic noise for a signal that refuses to fade. The search for a signal is a patient one, but the galaxy's own stars leave behind messages written in light, their final breath sculpted into some of the most beautiful objects in the cosmos. When a star like our Sun reaches the end of its life, it does not go quietly. It swells into a red giant, then sheds its outer layers in a gentle, glowing wind. The exposed hot core illuminates this expanding shell of gas, creating a planetary nebula. These are not the chaotic wrecks of supernova, but delicate, often shockingly symmetrical cosmic flowers. The Ring Nebula, for instance, appears as a near-perfect smoke ring in the sky, a luminous halo around a dying ember, yet this apparent simplicity is an illusion. For every classic ring or sphere we see, there are countless others with bewildering complexity. The Cat's Eye Nebula stares back at us with concentric shells and intricate jets. The Butterfly Nebula spreads magnificent, symmetrical wings across light years of space. We see hourglasses, intricate knots, and even structures with 4 lobes called quadrupolar nebulae. This is the profound mystery. Why does a star, which we assume is spherical, die in such spectacularly asymmetrical fashion? The serene death of a star should, in theory, produce a simple, expanding bubble. The fact that it so often does not tells us we are missing a crucial part of the story. The leading suspect in this cosmic sculpting is a hidden partner. Most stars in the galaxy are born in binary systems, and a companion star, even a small one, can dramatically choreograph a death. As the dying star puffs off its outer layers, the gravity of the second star can funnel that material into a dense disk around the pair. This disk then acts like a nozzle, collimating the outflow from the dying star's poles into 2 powerful, opposing jets. The result is not a sphere, but a magnificent bipolar nebula, a cosmic hourglass. In some cases, if the binary system is particularly complex or if the companion is itself a binary, the gravitational dance can even produce those rare 4-lobed shapes. But companions are not the only artists at work. The star's own magnetic field, twisted and amplified during its death throes, may also play a dominant role. Like an invisible hand, it can channel the outflowing gas into highly structured patterns, creating the intricate filaments and jets we observe. In many cases, it is likely a combination, a turbulent partnership of gravity and magnetism working in concert. The challenge is that we are seeing only a single, frozen moment in a process that unfolds over tens of thousands of years. We must deduce the entire life story of a stellar system from one snapshot of its spectacular death. Each of these nebulae is a unique masterpiece, a fossilized record of a star's final, turbulent years. Their overabundance of shapes, from simple rings to baroque butterflies, reveals a universe where spherical symmetry is the exception, not the rule in stellar death. This cosmic art gallery forces us to reconsider the quiet solitude of stars, hinting that their most beautiful moments often require a partner or the invisible architecture of their own magnetic souls to give them form. This elegant chaos of stellar death reveals a galaxy far from perfect symmetry, a truth seen in its very shape. Our classic image of the Milky Way as a flat, smooth spiral is an illusion. In reality, its outer disk is dramatically warped, twisted like the brim of a cosmic hat, and it flares outward, growing thicker at its edges. This is not a static sculpture, but a dynamic, rippling structure. The warp is most visible in the distribution of hydrogen gas and young stars on the galaxy's fringes. If you could view it from the side, you would see one side of the disk bending upward, while the opposite side curves downward, creating a distinct, gentle S-shape across tens of thousands of light years. What force could possibly twist an entire galaxy? The prime suspects are our largest satellite galaxies, the Large and Small Magellanic Clouds. These irregular dwarfs are not simply orbiting passively. They are on a plunging, elliptical path that brings them repeatedly through the Milky Way's outer halo. Each close passage creates a gravitational tug, a kind of persistent, rhythmic pull on our galaxy's vast disk of stars and gas. Think of it like dragging a stick through a still pond. The water ripples and distorts in the stick's wake. Over billions of years, these repeated tugs from the Magellanic Clouds have set the entire outer disk into a slow, majestic wobble, imprinting it with this permanent warp. Yet the mystery deepens when we add dark matter to the equation. Recent simulations suggest this dance is more complex. The Magellanic Clouds are not traveling alone. They are likely embedded within their own extensive halos of dark matter. As they swing through our galactic outskirts, their dark matter halos also pull on ours, creating a more pronounced and long-lasting distortion than the visible galaxies could alone. This makes the warp a potential probe, a way to weigh the invisible and map its influence through the very contortions of the stars we can see. Alongside the warp, we find the flare. Moving outward from the galactic center, the thin disk of stars and gas doesn't just end, it puffs up. The outer regions become noticeably thicker, like the edge of a fluffy pancake. This flaring is a natural consequence of gravity's weakening grip. In the crowded inner galaxy, the strong gravitational pull from the central bulge and dense disk keeps stars on very flat, orderly orbits. But in the sparse outskirts, that grip relaxes. Stars there feel less confining force, allowing their orbits to become more eccentric, to bob up and down through the galactic plane to a greater height. It is a galactic suburb where the rules are looser and the stellar paths are wilder. The enduring puzzle for astronomers is modeling this precisely. We must understand the exact timing, mass, and orbital history of the Magellanic Cloud's passages, while also accounting for the shape and response of our own galaxy's dark matter halo. Each new map of the warp's precise shape from missions like Gaia provides a stricter test for these cosmic simulations. This grand distortion is not a flaw, but a signature, a living record of the gravitational conversations our galaxy has had with its companions over eons, a reminder that even the mightiest spirals are not islands, but participants in a slow, beautiful, and bending ballet. This grand, bending dance of our galaxy is set against a stage that still bears scars from ancient violence. One of the most prominent scars lies shockingly close to home. Wrapped around a portion of our local spiral arm is a colossal, expanding bubble of gas known as the monogem ring. Also called the Gemini supernova remnant, this faint, nearly spherical shell of gas is over 200 light-years across. It is the ghost of a star that died in our own galactic backyard, a cosmic neighbor that met a cataclysmic end. The evidence suggests this supernova detonated a mere 1,000 light-years from Earth, which in galactic terms is practically next door. The event was so recent in cosmic time that its shattered remains are still rushing outward, shaping the very space our solar system now travels through. The age of this remnant, however, is a point of active debate. Some studies, based on the expansion speed of the gas and its current size, place the explosion at roughly 100,000 years ago. Others suggest it could be twice as old. Pinpointing the exact moment is crucial because it determines the story of our own local environment and perhaps even our planet's history. When that star exploded, it would have been a second sun in our sky for weeks, visible even in daylight. But its true impact was far more profound than light. The blast wave from the supernova would have flooded our region of space with intense radiation and a storm of high-energy particles. It would have compressed the local interstellar medium, the thin gas and dust between stars, possibly triggering the collapse of nearby clouds to form new stars. Our solar system, cruising through this region, would have been immersed in this altered environment. This leads to a gripping question: did this nearby stellar death leave a fingerprint on Earth itself? To answer that, scientists have turned to deep-sea geology, searching for a radioactive time capsule. When a massive star explodes, it forges rare isotopes not commonly found on Earth. One of these is iron-60, a radioactive form of iron with a half-life of 2.6 million years. If a supernova showered our planet with debris, traces of this alien iron-60 should have settled onto the ocean floor and been preserved in ancient crust. Remarkably, researchers have found precisely that. Layers of deep-sea sediment and fossilized bacteria mats dating to around 2.6 million years ago show distinct spikes in iron-60. This is a smoking gun, evidence that debris from at least one nearby supernova did indeed rain down on our planet. The monogem ring is a prime suspect for one of these events, though its estimated age is younger than that particular spike, suggesting our neighborhood may have experienced multiple such cataclysms. Could such an event have affected life? A sustained bath of cosmic rays from a nearby supernova could have increased radiation levels on Earth, potentially driving up mutation rates or damaging the ozone layer, allowing more harmful ultraviolet radiation from our own sun to reach the surface. Some scientists have proposed a controversial link between supernova-induced climate change and past extinction events or periods of rapid evolution. While proving a direct cause is immensely difficult, the presence of iron-60 in the geologic record is undeniable proof that we are not isolated. The history of our planet is written not only in its rocks, but in the stars that lived and died around us. The Monogam Ring is a silent, expanding monument to that connection, a reminder that the galaxy's violent creativity is part of our own story. The supernova's debris is a stark reminder that our place in the galaxy is defined by motion, a complex orbital dance with a surprising rule. There is a specific, critical distance from the galactic center where a star's orbital speed perfectly matches the rotation speed of the spiral arm pattern itself. This is the co-rotation circle, a theoretical boundary that should be a zone of chaos. Think of it like running on a moving sidewalk at an airport. If you match the sidewalk speed exactly, you stay in one spot relative to the floor around you. In galactic terms, a star at the co-rotation radius doesn't overtake or fall behind the spiral arms. It stays locked within the arm's gravitational influence indefinitely. According to long-standing theory, this is a terrible place for a star to be. The constant, unrelenting gravitational tug from the dense spiral arm should pump energy into the star's orbit, making it unstable. Over time, stars should be either kicked inward toward the galactic center or flung outward, effectively clearing out this region. The co-rotation circle, in theory, should be a gap, a stellar desert in the middle of the spiral disk. But when astronomers measured the actual distribution of stars in the Milky Way, they found the opposite. Instead of a gap, there is a pronounced peak in stellar density right at the co-rotation radius. It's not a desert, it's a thriving metropolis. This contradiction is a fundamental challenge to our models of how spiral galaxies work. How can a place of predicted instability be so densely populated? One compelling explanation turns the problem on its head. Perhaps the spiral arms don't just scatter stars, they can also trap them. This is the idea of resonant trapping. Just as a planet's gravity can trap asteroids at stable Lagrange points in its orbit, the combined gravitational field of the spiral arm and the galaxy might create a stable pocket at the co-rotation circle. Stars could be gently shepherded into this region and then held there, their orbits protected by the very resonance that was thought to destroy them. It's a cosmic balancing act of extraordinary precision. Another major factor is likely the giant bar of stars at our galaxy's heart. The Milky Way is a barred spiral, and this central bar rotates, creating its own powerful gravitational rhythms. The influence of the bar could completely reshape the dynamics near co-rotation, creating zones of stability that overlap with the spiral arm's influence. The peak we see might not be caused by the spiral arms alone, but by a complex gravitational duet between the bar and the arms, a harmony that builds up stars instead of scattering them. This single observational fact, a density peak where a gap was predicted, forces astronomers to rewrite the rules of galactic traffic. It shows that the spiral arms are not just passive patterns, but active architects, capable of both construction and destruction on a galactic scale. The co-rotation circle mystery proves that our map of the Milky Way is still being drawn, and some of its most important landmarks exist where we once believed nothing could survive. The stability of our galactic neighborhood is a recent luxury, a calm chapter in a far more violent biography. Our galaxy's halo is a cosmic graveyard filled with ancient, wandering ghosts. These are the oldest stars in the Milky Way, suns that burn with a faint, primordial light. Unlike the rich, metal-filled stars of the bustling disk, these halo stars are metal-poor, containing only traces of elements heavier than hydrogen and helium. Their very composition is a clue, telling us they were born from nearly pure Big Bang material in a time before countless supernovae had enriched the cosmos. They are not just old, they are fossils, and their silent orbits hold the memory of our galaxy's brutal childhood. For decades, these stars seem to move in random, plunging orbits around the galactic center, a chaotic swarm. But with the arrival of the Gaia Space Observatory, that picture shattered. Gaia has provided exquisitely precise maps of the positions and motions of over 1 billion stars, and in that data, a hidden story emerged. The motions of these ancient halo stars are not random at all. They are grouped into distinct rivers and streams, like different families of fish all swimming together in a vast ocean. These are stellar streams, the shredded remains of smaller galaxies that ventured too close to the young Milky Way and were torn apart by its gravity. The most dramatic of these fossilized collisions has been nicknamed the Gaia Sausage, or sometimes Gaia Enceladus. It is not a visible object but a pattern. Gaia revealed that a huge population of ancient metal-poor stars in the halo share a very peculiar motion. They orbit on highly elongated radial paths, plunging directly toward the galactic center and then swinging far out again like bees swarming a hive. This unique orbital fingerprint is the signature of a single colossal merger that happened roughly 10 billion years ago. A dwarf galaxy, perhaps 1/4 the mass of the Milky Way's disk at the time, made a fateful approach. It did not just pass by, it was utterly consumed. The gravitational tides of our galaxy stretched it into a long stream of stars that then wrapped around the core, eventually mixing to form a significant portion of the inner halo we see today. This event was likely the last major act of galactic construction, fundamentally shaping the Milky Way's size and structure, but the sausage is not the only ghost at the feast. The halo is a layered archaeological site. Fainter, more delicate streams crisscross the skies, each the dissolving ribbon of a smaller victim. There is the Helmi stream, the Sagittarius stream, and many others still being catalogued. Each stream has its own distinct chemical signature, a specific ratio of elements that acts like a DNA test, tracing its stars back to a common parent galaxy. By reading this chemical fingerprint and reconstructing the orbital paths, astronomers are performing galactic forensics. They are piecing together a timeline of cannibalism, determining which galaxy was consumed first, which merged later, and how each collision added its own unique stars to the halo's population. The grand mystery now is sequencing this violent history. Did the Milky Way grow steadily by snacking on many small galaxies, or was its growth dominated by a few gigantic meals like the Gaia Sausage? How did these mergers trigger waves of star formation or influence the growth of the central black hole? Every new stellar stream mapped by Gaia adds another piece to the puzzle. We are learning that the serene spiral we see today is the product of a chaotic and destructive past, a cosmic collage built from the ruins of its neighbors. The silent, ancient stars of the halo are the witnesses, and their slow, patient orbits are finally beginning to testify. These ancient stellar witnesses provided the first reliable map of our galaxy's vast scale. For over a century, astronomers have depended on a special class of stars as their primary cosmic yardsticks, the Cepheid variables. These are pulsating giants, stars that rhythmically brighten and dim over periods of days or weeks. In the early 1900s, Henrietta Swan Leavitt discovered their crucial secret, a direct and predictable relationship between a Cepheid's pulsation period and its true intrinsic brightness. A Cepheid that takes 10 days to cycle from bright to dim and back is always on average about 7,000 times more luminous than our Sun. One with a 30-day period is even brighter. This period luminosity relationship was a revelation. By simply measuring how fast a Cepheid pulsed, astronomers could calculate its true power. Then, by comparing that to how dim it appeared in the sky, they could determine its distance with remarkable precision. Cepheids became the foundation stones of the cosmic distance ladder, the first crucial step in measuring the scale of the Milky Way and later the expansion of the universe itself. Yet this trusted ruler has begun to show cracks. Across the galaxy, astronomers are finding cepheids that break the rules, stars that pulse with a rhythm that promises one brightness but shine with another. These are the anomalous cepheids, and their misbehavior threatens to subtly warp our entire map of the cosmos. If a standard candle flickers unpredictably, how can we trust any measurement built upon it? The hunt for an explanation has led down several fascinating paths. The first possibility is that these stars are not classical cepheids at all, but belong to a different, older population. Classical cepheids are relatively young, massive stars born from metal-rich gas in the galaxy's bustling disk. But there exists another family called Type II cepheids, which are older, less massive, and follow a different, fainter period luminosity relationship. Could some anomalous stars simply be these older interlopers, mistakenly identified? Careful studies of their chemical compositions and locations within the galaxy are helping to sort this out. A second, more dynamic explanation involves cosmic companionship. Many, if not most, stars are born in binary systems. What if an anomalous cepheid is not alone? If it has a companion star, the light we see is a blend of two sources. The cepheid itself might be faithfully following the period luminosity law, but the extra light from its dimmer partner makes the combined system appear brighter than expected for its pulse rate. Untangling this stellar duet requires exquisitely precise observations, often using the wobble in the cepheid's motion to infer the hidden companion's gravitational pull. Perhaps the most profound possibility involves the star's very ingredients. The classical period luminosity relationship was calibrated using cepheids in our local galactic neighborhood. But what if cepheids born in different environments with different amounts of heavier elements pulsate differently? A cepheid formed in the early universe or in a dwarf galaxy with much lower metallicity might have a slightly different internal structure, altering how heat moves through its outer layers and changing the precise link between its pulse and its power. This would mean our one-size-fits-all ruler needs different calibrations for different cosmic neighborhoods. The stakes of this mystery could not be higher. Cepheid variables are the critical first step in measuring the Hubble constant, the rate of the universe's expansion. Discrepancies in cepheid distances contribute directly to the current tension in cosmology, where measurements of the universe's expansion rate from nearby galaxies disagree with predictions based on the ancient cosmic microwave background. Are anomalous cepheids introducing a subtle error into our local measurements? Solving their puzzle is not just about understanding a few odd stars. It is about verifying the fundamental yardstick by which we measure the scale and fate of everything we see. Our galactic yardstick depends on stars whose behavior we thought we understood, but right in our own stellar neighborhood, an even more local mystery stares back at us. Surrounding our sun is a grand, tilted ring of brilliant young stars and stellar nurseries known as the Good Belt. This is not a distant structure, it is our local cosmic architecture. If you look at the night sky, many of its most famous jewels are part of this belt. The Sword of Orion, the glowing heart of the Scorpius constellation, and the Pleiades star cluster all belong to this vast, inclined ring. It is about 3,000 light-years across, and it is cocked at a distinct 20-degree angle to the flat plane of the Milky Way's disk. We are essentially living inside a slightly warped local bubble of stellar activity, and no one is entirely sure how it got here. The Good Belt is not just a random assortment of stars, it is a coherent structure, a wave of star formation that has swept through our local patch of gas within the last 30 to 50 million years. Its stars are predominantly young, hot, and massive, the kind that live fast and die young in brilliant supernova. The mystery is what set this entire process in motion. What triggered this local burst of creation, tilting it away from the galaxy's orderly disk? one compelling theory points to an ancient stellar catastrophe. Imagine a massive star or even a binary pair that lived and died in our vicinity long before the good belt existed. Its final supernova explosion would have sent a powerful shockwave rippling through the surrounding interstellar cloud. This expanding shell of gas and pressure could have compressed the cloud in a specific, off-kilter way, initiating a cascade of star formation that propagated in a ring, much like a stone dropped in a pond creates circular waves. The tilt could simply be a relic of the explosion's asymmetrical location relative to the galactic plane. Another hypothesis involves a more direct collision. A high-velocity cloud, a massive blob of primordial hydrogen gas falling into the Milky Way from the halo, could have slammed into our region of the galactic disk. The impact would have been a monumental event, compressing the gas and triggering a wave of star formation that rippled outward from the point of impact. The cloud's trajectory, coming in from above or below the plane, would naturally impart the tilted angle we observe in the resulting stellar ring. Perhaps the most exotic idea invokes the invisible hand of dark matter. Could a small, dense clump of dark matter, a subhalo, have passed through this region of the galaxy millions of years ago? Its gravitational tug, though unseen, could have stirred up the gas, concentrating it and initiating the collapse that led to the belt's formation. As the dark matter clump moved on, it would have left behind this tilted ring of young stars as the only evidence of its passage. Each explanation paints a different picture of our local cosmic history. Was it a brilliant death, a violent impact, or a ghostly gravitational encounter? The good belt is a crime scene in our own backyard, and the young, bright stars are the evidence. Solving its origin would tell us not just about the forces that shape star formation, but about the specific, dramatic events that crafted the stellar landscape we call home. This grand, tilted ring of local stars offers a poignant perspective on our place in the cosmic story. All of these mysteries, from the warp of the galaxy to the pulses of dying stars, converge on a single, profound question. Are we the only ones here to wonder about them? This is the final and greatest enigma of the Milky Way. Given the staggering scale of our galaxy, with its hundreds of billions of stars and likely trillions of planets, the silence is deafening. This contradiction is known as the Fermi paradox, a simple, haunting query: where is everybody? If life and intelligence are common, the galaxy should be teeming with civilizations, their signals and artifacts obvious. Yet we hear nothing but cosmic static and natural radio whispers. One chilling answer to this silence is the Great Filter hypothesis. It suggests that somewhere between the emergence of simple chemistry and the rise of a galaxy-spanning civilization, there exists a barrier, an evolutionary or technological step so improbable or so dangerous that almost every potential civilization fails to cross it. The terrifying implication is that we do not know if this filter is behind us or still ahead. Perhaps the very galactic mysteries we have explored are the components of this filter. Maybe the galactic habitable zone is far narrower and more fleeting than we hope, with planets routinely sterilized by gamma-ray bursts from those brilliant, deadly supernovae. Perhaps the gravitational chaos from stellar flybys or dark matter subhalos frequently disrupts planetary systems, hurling promising worlds into frozen darkness long before intelligence can arise. Or maybe the stability required for billions of years of evolution is a cosmic rarity, shattered by the kind of cataclysmic mergers that built our galaxy's halo. Each mystery we solve could reveal another lock on the gate. Our search for an answer is now a two-pronged galactic investigation. The first is the hunt for biosignatures, the chemical fingerprints of life itself. We are learning to read the atmospheres of distant exoplanets, looking for unstable combinations of gases like oxygen and methane coexisting that would almost certainly require biology to maintain. A single, unambiguous detection of such a signature on a rocky world within a star's habitable zone would revolutionize our understanding of life's place in the cosmos, proving the first steps are possible. The second, more elusive search is for technosignatures, the markers of technology. This goes beyond listening for radio signals. We might someday detect the unnatural glow of city lights on a planet's night side, the spectral signature of industrial pollutants in an exosphere, or even the shadow of a vast megastructure partially obscuring a star. Every anomalous flash, every unexplained atmospheric compound becomes a clue. Framed by the galaxy's violent history and delicate balances, this search is the ultimate detective story. We are sifting through the evidence of 400 billion star systems, looking for a single clue that we are not the only detectives on the case. The answer, whether it arrives as a chemical whisper in a telescope's data or a structured signal from the void, will forever change the meaning of every other mystery in the Milky Way. It will tell us if the cosmos is a cathedral of wonder meant to be explored, or a beautiful, empty monument to our own astonishing loneliness. This galactic silence is not an end but an invitation. From the sleeping giant at our core to the phantom pull of the great attractor, from stellar bullets to phantom planets, we have journeyed through a cosmos defined more by questions than by answers. Each mystery, whether writ large across the Fermi bubbles or etched in the faint pulse of a Cepheid variable, is not a barrier to knowledge but a beacon. It is the unknown that propels our science forward, that turns data into discovery and observation into profound awe. The Milky Way is not a static map but a living story, and we are only now learning to read its chapters. Every time you look up at that river of stars, remember you are gazing at a tapestry of enigmas. You are seeing the warp, the unseen halo, the ancient streams of galactic cannibals, and the quiet neighborhoods where life might just be taking its first tentative steps. Our understanding is a flickering candle in a vast cathedral of darkness, and that is what makes the pursuit so magnificent. The next great revelation is out there, waiting in the next dataset, the next telescope image, the next whispered signal from the void. So keep looking up with wonder and keep questioning everything. Which of these 25 mysteries captures your imagination the most? Let us know in the comments below. And if you want to continue exploring the universe's deepest secrets with us, be sure to subscribe. Our cosmic journey is just beginning.